We are now ready for Module 5. Up until now, we have been looking at trig functions and determining the trig function of various angles. And once again, I want to reemphasize, since the midterm exam in this class will be coming soon, you really need to know the unit circle. That's the easiest and best way that we determine trig functions. For example, if I say, what is the sine of (4 pi over 3)? 4 pi over 3 is one of my special angles. It's in radians. What do? I go in my head, although I'll show you here. I think unit circle, here's how I think. I know this 3 denominator is one of these 4 points right here. Those are the ones with the 3. 4 pi over 3, I know is right here. And then for this point, since it's a sine, I'm looking for the value of y. I know the value of y is the square root of 3 over 2. And since it's in the third quadrant, it's negative. So hopefully within just a few seconds, how about the cosine of what is the cosine of 405 degrees? Well, the first thing I realize is all the way around the unit circle is 360 degrees. So really, if I take 405 minus 360, really, this becomes a problem of what's the cosine of 45 degrees. 405 degrees and 45 degrees are coterminal angles. It's really the same angle. So now unit circle, I realize 45 degrees is right here, and I'm looking for the value of x, and I remember it's square root of 2 over 2. Now what we're going to do here in Module 5, we are going to sort of flip this around. What do I mean by that? So far, up until now, you've been given an angle, and then we found various trig functions. That's what we did here. Now we're going to flip that around, and I'm going to say something like this. This is almost like an equation. The sine of theta equals 1. I want to solve for theta. So now we're given a number, and we have to go back and find the angle that, when you take the sine of that angle, produces the number 1. So now you think to yourself, okay, I'll write it down here. For what angle, which I'm going to call theta, does the sine for what angle does the sine result in 1? What angle, when you take the sine of it, gives you an answer of 1? Once again, in your head, you should be thinking of the unit circle. Here it is up here. Where in the unit circle is the sign 1? Well, once again, the sign is the value of y. So where in the unit circle is y1? Right here, right? What's that angle? Well, we have a choice. We can either give the answer in radians or degrees. Let's do it in radians. The answer is pi over 2. Although let me give you a quick little sneak preview of something we're going to have to take into account. Are there any other angles where the sine of that angle is 1? Let me give you an idea. How about pi over 2 is right here. However, how about if I go around the circle once, which is 2 pi, and then go pi over 2 more? I think that ends up being 5 pi over 2. So is that correct? Is the sine of 5 pi over 2 equal to 1? Yeah, it is. So I've actually got 2 angles for a solution. As a matter of fact, theoretically, how many angles would solve this equation? Theoretically, an infinite number, right? You could just keep going around and around the unit circle. As long as you stop here, the sine of that angle is going to be 1. So what they oftentimes will do when they give you a problem like this, here's what they'll do. They'll say, they'll put a limitation on the angle, and usually they'll say, okay, let's just look at angles between 0 and 2 pi. And then they say, so then solve this equation. So when they limit it like this, then there actually would only be one answer. Let's do another example. How about and now I'm going to go ahead and limit this to just 0 to 2 pi. So now you ask yourself the question, to solve this equation, I need to go find an angle so that when I take the cosine of that angle, it equals negative square root of 3 over 2. So what am I doing? I'm really going to my unit circle, and I'm saying, where on this unit circle is the cosine negative square root of 3 over 2? Now the cosine is like the x value of the points. So then in terms of the unit circle, I remember, oh, those are the sort of the pi over 6 points. There are 4 of them, because I know at those points the cosine is square root of 3 over 2. However, I want it to be negative square root of 3 over 2, and I realize there are actually 2 angles. The first one is 5 pi over 6. The cosine of 5 pi over 6 is negative square root of 3 over 2. But then also, there's a second angle, 7 pi over 6. So for this little equation, there are actually 2 solutions when we're looking between 0 and 2 pi. So that's the kind of thing we're going to look at now. Now let's go ahead. I'm going to show you how. Let's go back now and let's account for the idea being all the different solutions we go round and around. So let's go ahead Here's how we do that. Let's choose another one. Let's say we're asked to solve this equation, and there's no limit on the angle. As a matter of fact, sometimes the wording I use, I would say give solution, and I use this word general form. In other words, somehow I want to write my solution so that all the possible angles are represented. All right. Here's how we do that. Let's first ask ourselves, let's go find the first angle that we can think of, the smallest angle where the sine of pi is 1/2, the sine of theta is 1/2. So let's go find an angle that when I go take the sine of that angle, it's 1/2. So once again, in my head, I'm going to the unit circle, and I'm going to try to find some of my special angles where the sine is 1/2, which means where the y value is 1/2. And the first one I can think of is pi over 6. Of course, you realize pi over 6 is right here. So that is a solution. But then I think, I could go to pi over 6, but then I could go around the unit circle and go pi over 6 more and get a solution. I could go around the unit circle twice and then move up to pi over 6, and that would be another solution. I mean, I could do this. I could just keep going around the unit circle. How would I write that? How could I express that so everything is covered? And here's how we do it. If you think about it, we got pi over 6, and then for the next one, what do? We go all the way around 2 pi, and then we go pi over 6. And then for the next one, we go all the way around twice, and then go pi over 6. Well, here's how we could express that. You take pi over 6, and we're going to add it to 2 pi is the distance we always go around the circle before we go our last pi over 6. However, I'm going to multiply it by k, where k equals, this is a little tricky, k basically is like an integer. Normally, I'll just write it like this, where k is 0, then 1, then 2, then 3. Although there are some special cases where k can even be a negative number. So just so you know, we could also have -1, -2. It's pretty rare that the k's are negative. Usually we just think about k's being 0, 1, 2, 3. What does that mean? This equation means you plug in 0 for k, 2 pi times 0 is 0. My first solution is pi over 6. If I want to get the next solution, I now plug in k equals 1. So if I have k equals 1, 2 pi times 1 is 2 pi. Pi over 6 plus 2 pi would be 7 pi over 6, and that is my second solution. If I want to get another solution, I plug in k equals 2. 2 pi times 2 is 4 pi. 4 pi plus 5 over 6 is like, what, 25 pi over 6? In other words, you can keep going forever. So this is a way that we can write the solution that actually covers all the different possibilities. However, what's interesting is this solution here covers all sort of what we could call the pi over 6 solutions. But there's actually another angle where the sine of theta is 1/2. And what is that? It's actually over here. 5 pi over 6. So what we do is we actually write then the second possibility, and we use the same principle. 5 pi over 6 is a starting point. However, we can keep going around and around the unit circle. So as a general solution, these are the general solutions. This will be on the homework. They're going to ask you to give the solutions that they're going to talk about, including the K. And this is what they're talking about. Now, most of the time, when they give you this problem, they will say for theta between 0 and 2 pi, solve so when they limit the angles, then you just think to yourself, okay, one trip around the unit circle, what angles would the sine be 1/2? And then, of course, you say that's your solution. So this I sort of call specific because it's very narrow, the possible solutions. I like to call this general, where this theoretically covers all the solutions to this equation. So if I were to do I'll make a note, give general solution. And let's say, how about for give the general solution for cosine of theta equals square root of 2 over 2. What you do is you make one trip around the unit circle and figure out which angles does a cosine equal square root of 2 over 2. The first one you come across is pi over 4. Now, as soon as I get a solution like that, I just go ahead and right away add on the 2 pi k. And then I think, well, are there any more angles on the unit circle where the cosine is square root of 2 over 2? And I say, yeah, down in that fourth quadrant, the 7 pi over 4, the cosine of 7 pi over 4 square root of 2 over 2, and then I just tack on the plus 2 pi k. Now, if they'd ask me if they said, hey, just limit it to 0 to 2 pi, and of course my solution would be pi over 4 and 7 pi over 4. Now let me do one little bit of a twist. How about they may give you an equation for the tangent. How about they want you to solve this tangent of theta equals square root of 3. Now this is a little tricky on two fronts. First front is to find tangents. What I usually do is, in my mind, of course, I convert it to sine over cosine. So I'm thinking of the unit circle, and I'm thinking of taking the sine of an angle and dividing it by the cosine of that angle, and it has to be square root of 3. And, normally that happens when you have maybe square root of 3 over 2 over 1/2. Because that's the y and that's the x of some point on my unit circle. Now if I want to get the general solution, let me just explain this to you. So what's the angle where this occurs? What's the angle where the sine is square root of 3 over 2 and the cosine is 1/2? Should be pi over 3. Now what's interesting, if you ask yourself, is there another angle on the unit circle that equals square root of 3 over 2? And there is. If you go into third quadrant, let me just call this specific for now. Specific solutions. One trip around the unit circle, 0 to 2 pi, there are two solutions for this. But if they want the general, in other words, include the k's, what's interesting is, for tangent, normally for sine and cosine, I had to write them separately and add on 2 pi k to each one. Right? Here's the one for the sine. Did them separately. Just the way it works out for the tangent, even though once again I've got two solutions on one trip around the unit circle, as it turns out, you don't actually have to write them separately. You can just write the first one, and instead of adding 2 pi times k, it works out for the tangent, we could just have one solution, and we make pi times k. So if k is 0, you get pi over 3. If k is 1, you get 4 pi over 3. If k is 2, then you get 7 pi over 3, which is another answer. So it turns out when you do tangents, you just add on pi times k. Where sine and cosine, it's 2 pi times k. All right, now let me give you the next twist in solving these kinds of equations. If you notice, you probably didn't think about it, but now I'm going to point out all the little problems I've done. Matter of fact, just let me do one more. Here's the kind of problem you'll have. Sometimes they just make you do a little bit of math. They say, solve this equation for theta. 2 sine theta now, unless I say from now on, as I'm solving these equations, I'm going to limit the answer, the angle, to 0 to 2 pi. So I'm not going to write it every time, but I'm going to limit my answer from 0 to 2 pi. So here's this equation. They want to solve for theta. I've always taught this is like a two-step process. The first step is I want to get the trig function by itself on one side. All right, I want the trig function by itself on one side. So in order to do that, first thing I'm going to do is I'm going to subtract 3 from both sides. If I want to get the trig function by itself, I need to get rid of this 2. Since it's 2 times the trig function, what do I do to get rid of the 2? Divide both sides by 2. So when you do that, now you finally have the trig function by itself. Sine theta equals negative 1/2. So that's the first step. First step, get the trig function by itself. Maybe I should write it down. Get trig function by itself. And then the second step is then solve for your angle. So once I get the trig function by itself, now I can do what we've been doing so far in this lesson. I ask myself, okay, let's go find all the angles from 0 to 2 pi where the sine is -1/2. And I think to myself, okay, the sine is 1/2 at the pi over 6 points, and I need the negative ones, so it's going to be down there in the third and fourth quadrant. So it's going to be 7 pi over 6 and 11 pi over 6. And there's my solution. One more quick one. Once again, we're asked to solve this equation for theta. We're trying to find the angle that makes this equation true. First step, get the trig function by itself. I'll add 1 to both sides. Divide both sides by 4. Here's what's interesting. I've got the trig function by itself, although you notice it's squared. Well, I don't really want to, if I want to solve for this, I really want it to be cosine theta, not cosine squared theta. So what can I do? What can I do to change this cosine squared theta to cosine theta? Well, since it's over here by itself on one side, how about anytime you have something squared and you want it to not be squared, you have to take square root. Of course, I have to do the square root of both sides. So square root of cosine squared theta is cosine theta. Square root of 1/4, think about it, you can take the square root of the top, which is 1, square root of the bottom, which is 2. But here's something students always forget. Whenever you take the square root of a number, you actually have to put down plus or minus. Those are both, square root of 1/4 is plus or minus 1/2. Because the square root of 1/4 says, find a number that multiplied by itself twice equals 1/4. Well, -1/2 multiplied by -1/2 equals 1/4. So therefore now, how does this work? Well, let's first go find the angles for positive 1/2. And quickly in my head, I remember it's pi over 3 and 5 pi over 3. So those are the ones that come from the positive 1/2. But then I say, okay, now let's also go look at the angles where the cosine would give me -1/2. And that ends up being 2 pi over 3. This is quadrant 2. And quadrant 3, 4 pi over 3. There's actually 4 solutions. There are 4 angles. If you plug any one of these angles into this original equation, it'll work. There are actually 4 solutions. All right, so those are some of the kinds of problems you're going to have. Now, let me give you one more twist on these problems, and then we'll start another video. So far, every kind of equation I've solved, I want you to notice something. I started out way back here with sine theta equals 1. Sine theta 1/2. I did cosine theta, -square 3 over 2. These are all my notes. Sine theta 1/2. Cosine theta square root of 2 over 2. Even when I had some equations, I eventually got to the point where it was sine theta -1/2, cosine theta equals plus or minus -1/2. The thing I want you to notice is, for all those problems, what was inside the trig function just theta by itself. Right? Sine theta, cosine theta. I even did a tangent of theta. Now here's a twist. Here's an equation they want us to solve. The sine of 3 theta equals -1. In other words, inside the trig function is not just simply theta. Now it's 3 theta, and that causes some complications. Matter of fact, I'm going to solve this one, and then I'm going to solve another one in a minute that's very similar. It looks more complicated. Here's another equation. Cosine of the quantity theta divided by 3 minus pi over 4, all that equals 1/2. For both of these, we're trying to solve these equations, which means find the angle theta that works for these equations. For both of these, the way we're going to go by solving them is by using, we're going to call it U substitution. Maybe you've done some U substitution for other kinds of problems before in algebra. So here's the idea. Let me do this first one, the sine of 3 theta. U substitution says, instead of working with this theta, 3 theta, I take whatever is inside the trig function. And I'm going to call whatever is inside the trig function, I'm going to call it u. So like I introduced this new variable u. So therefore, I'm going to rewrite this equation. Instead of sine of 3 theta equals -1, I'm going to make it sine of u equals -1. And now, if you look here, inside the trig function, all I have is just my one variable, just like I used to have. I can go ahead and now solve this equation. But let me warn you, when I solve it, I have to write it in the general form. I have to include the 2 pi k's in order to really make sure I don't mess up on this. So let's think about this. Okay, so I'm looking for an angle. I'm going to call the angle u. I'm looking for an angle u where the sine is -1. So one trip around the unit circle, that only occurs once, and that's when the angle is 3 pi over 2. Once again, how did I know that? From the unit circle. And in my head, I can visualize a unit circle. Maybe on the test, one of the first things you'll want to do is take your scratch paper and write out the unit circle. And then every time you need to look up an angle, you can just grab your scratch paper. However you want to do it, you have to know that. But now, I want to go ahead and have the general solution. So now I've sort of solved this equation. I have an answer for u. But the problem is I want to find the answer for theta. What I do, once I have now gotten a solution for u, I now want to take that solution for u and somehow convert it back to theta. And the way I do that is I go back and I get my original definition of u. When I first defined or first introduced u, I said u equals 3 theta. Now here is also my solution for u. So u also equals this, so let's write this out. Now, if I take these two parts here, and if I solve for theta, in other words, if I get theta by itself, then I will have solved, I'll have the general solution of the equation. What do I have to do? Looks like I have to divide both sides by 3. And when I do that, of course this simplifies. So here's my, let me write it like this. Here's my general solution. Now if they ask me, for just the angles between 0 and 2 pi, here's how I do this now. I've got this solution with this k. What I do is I start putting in my numbers for k and finding my solutions. In other words, k starts out, I'll put in 0 first. When I set k equal to 0, what does theta equal? Well, 0 times this is 0. So there's my first solution. But there might be more solutions. So then I stick in k equals 1. Remember, k is 0, 1, 2, 3, 4. And matter of fact, we might even need to check k equals minus 1. Maybe we'll do that just to make sure. So when k is 1, what do I have? 2 pi over 3 plus pi over 2. I actually have to do a little bit of math to see what that equals. I have to get a common denominator. 3 pi over 6 plus 4 pi over 6. Looks like 7 pi over 6. Is 7 pi over 6 between 0 and 2 pi? Yes, it is. So there's another solution. And I have to actually keep moving up this number of k until my solution is bigger than 2 pi. Then I stop. What happens when k is 2? Then I have 4 pi over 3 plus pi over 2. Let's see what that equals. That's going to be 8 pi over 6 plus 3 pi over 6. That looks like 11 pi over 6. Wow. I have to keep bumping up the k until my angle gets bigger than 2 pi. Then I can stop. When k is 3, well, that's easy because this is going to be 2 pi plus pi over 2, which is 5 pi over 2. Then you notice all of a sudden my angle is larger than 2 pi, so I stop here. I don't have to keep going because now I'm out of where they want the answer to be. Just for fun, there are occasionally a problem where you have to set k equal to a minus 1 and see what happens. But in this case, if I have negative 2 pi over 3 plus pi over 2, it ends up being like a negative angle, which is less than 0. So once again, that doesn't work. So it looks like, I forgot to write this, looks like there are 3 solutions to this problem. All right, so that was pretty tricky. So once again, the whole key was, since I have some numbers, some extra stuff inside the trig function, I have to introduce the variable u and go through these steps. Let me go and do one more. Remember, I had another problem that looked even more complicated, and that was this one. Cosine theta over 3 minus pi over 4 equals 1/2. And of course, they're saying, please solve this equation for theta. Once again, because I have all this extra stuff inside my trig function, I cannot solve it directly. Instead, I take everything inside the trig function and I call that u, or I can say I define that to be equal to u. So then I can get rid of all this mess and rewrite my equation as just cosine u equals 1/2. And now I can solve this equation for u. So I ask myself, what are the angles go around unit circle where the cosine is 1/2? The first one is pi over 3, and of course I have to do the general equation. But then there's another one in the fourth quadrant, 5 pi over 3. So these are my solutions for u, but of course that's not really what I want. In the end, I want a solution for theta. So now, let's take my first solution for u. So here's my definition of u. And I'm going to take my first solution for u and write it here. And I'm going to solve this messy thing for theta. Wow. I guess first thing I'll do is I'll add pi over 4 to both sides. Now if I add pi over 4 to pi over 3, this is 3 pi over 12. This is 4 pi over, I think it's 7 pi over 12. But of course I want this to be theta, so I'll multiply both sides by 3. And I believe this ends up being 7 pi over 4 plus 6 pi k. Seems a little crazy. Now that's my solution from my first u. I have to do the same thing for the second u. This is a really messy problem. And I apologize if I make some math errors. What I'm teaching you is correct if I make a math error. Sorry about that, but I make errors too. So now I have to add pi over 4 to both sides. I guess this is 3 pi over 12, and this is 20. I'm really taking a chance by doing this in my head, but multiply 3 both sides, 23 pi over 4 plus 6 pi k. So here, if I didn't make any math errors, so now, if I go over here and start counting my k's, let's go up here first. If I'm looking for 0 to 2 pi, whoops, I keep doing that. K is 0. I get 7 pi over 4. When k is 0 down here, I get 23 pi over 4. That's already bigger than 2 pi, so I'm already done here. You can see when I stick k equal to 1 up here, I've already got 6 pi plus this, so I'm already done there. The only possibility might be to check about -1, but 7 pi over 4 plus a -6 pi, that's going to be a negative. This one I'm not sure about. Let's check that out. 23 pi over 4 minus 6 pi. oh, this is 24 pi over 4, 23 pi over 4. It's negative pi over 4. Looks like there's actually only going to be, with all that work, if I didn't mess up, there's actually only one solution. That was sort of messy, but the idea here is now, my initial problem, because I had a bunch of stuff inside the trig function, I had to do my u substitution. So once again, the two examples were this first one, which is easier, sine of 3 pi equals negative 1. I had to do the u substitution. I don't even know where I set my paper. But then, oh, here it is. Did the u substitution and got my solution. Second one was even messier, but I finally got my solution. All right, so this is the first part of Module 7. Now, I'm going to make another video where we talk about something called inverse trig functions, which relates very closely to what we're talking about now.